we'd like to define a nicer interface for our program. While we could manage something ourselves with getArgs and pattern matching, it's easier to get good results using a library. We'll use a package called optparse-applicative, which provides us with an EDSL, yes, another one, to build common arguments parsers. Things like commands, switches, and flags can be built and composed together to make a parser for command line arguments without actually writing operations on strings, as we did when we wrote our markup parser. And will provide other benefits such as automatic generation of usage lines, help screens, error reporting, and more. While optparse-applicative's dependency footprint is not very large, it's likely that a user of our library would not need command line parsing in this particular case. So it makes sense to add this dependency to the executable section rather than the library section in the Cabal file. The optparse-applicative package has pretty decent documentation, but we'll cover a few important things to pay attention to in this chapter. In general, there are 4 important things we need to do. Define our model. We want to define an ADT that describes the various options and commands for our program. 2. Define a parser that will produce a value of our model type when run. 3. Run the parser on our program arguments input. And 4. Pattern match on the model and call the right operations according to the options. Let's envision our command line interface for a second. What should it look like? We want to be able to convert a single line or input stream to either a file or an output stream, or we want to process a whole directory and create a new directory. We can model it in an ADT like this. 2 options: convert a single file from single input to single output, and convert directory from file path to file path. Single input and single outputs are similar. It's either standard input or standard output or a file path to a file. And note that we could have technically also used maybe file path to encode both single input and single output, but we would have to remember what nothing means in each context. By creating a new type with properly named constructors for each option, we make it easier for the reader of the code to understand the meaning of it. In terms of interfaces, we could decide that when a user would like to convert a single input source, they would use the convert command and supply the options flags for the input file path and the output file path to read or write from a file. When the user does not supply one or both flags, we will read or write from the standard input or standard output accordingly. If the user would like to convert a directory, they can use the convert directory command and supply the 2 mandatory flags for the input file path and the output file path. This is the most interesting part of the process. How do we build a parser that fits our model? The optparse-applicative library introduces a new type called parser. Parser, similar to maybe an IO, has the kind type to type. When it's applied with a saturated or concrete type, such as int, bool, or options, it can become a saturated type, one that has values. A parser A represents a specification of a command line option parser that produces a value of type A when the command line arguments are successfully parsed. This is similar to how IO of A represents a description of a program that can produce a value of type A. The main difference between these 2 types is that while we cannot convert from IO of A to an A, and we just chain IO operations and have the Haskell runtime execute them, we can convert a parser A to a function that takes a list of strings representing the program arguments and produces an A if it manages to parse the arguments. As we've seen with previous EDSLs, the library uses a combinator pattern as well. We need to consider the basic primitives for building a parser and the methods of composing the small parsers into bigger parsers. Let's see an example of a small parser. String option is a parser builder. It's a function that takes a combined option modifiers as an argument and returns a parser that will parse a string. We can specify the type to be file path because file path is an alias to a string. The parser builder describes how to parse the value, and the modifiers describe its properties, such as the flag name, the shorthand of the flag name, and how it would be described in the usage and help messages. Well, actually, string option can return any string type that implements the interface is string. There are a few such types, for example text, a much more efficient Unicode text type from the text package. It's more efficient than string because while string is implemented as a linked list of characters, text is implemented as an array of bytes. Text is usually what we should use for text values instead of string. We have not been using it up until now because it's slightly less ergonomic to use than string, and we don't actually need it to learn Haskell at the beginning, but it's often the preferred type to use for text. As you can see, modifiers can be composed using append function, which means modifiers implemented as an instance of semi-group type class. With such an interface, we don't have to supply all the modifier options, only the relevant ones. So if we don't want to have a shortened flag name, we don't have to add it. For the data type we've defined, having parser of file paths takes a good step in the right direction, but it's not exactly what we need for convert single. We need a parser for single input and a parser for single output. if we had a file path, we could have converted it to single input by using the input file constructor. Because remember, input file is also a function. However, to convert a parser, we need functions with these types. We need to go from a parser or file path to the parser of single input and the output. Fortunately, the parser interface provides us with a function to lift a function like file path to single input to work on parsers, making it a function with the type parser or file path to a parser of single input. Of course, this function will work for any input and output, so if we have a function with the type a to b, we can pass it to the function and get a new function of the type parser a to parser b. This function is called fmap. We've seen fmap before in the interface of other types, on the lists, IOs, and now on parsers. Fmap is a type class function like append and show. It belongs to the type class functor. And it has the following laws. The identity law, which says that if we don't change the values, nothing should change. And the composition law. Composing the lifted functions is the same as composing them after fmap. Any type f that can implement fmap and follows these laws can be a valid instance of functor. And notice how f is a kind type to type. We can infer the kind of f by looking at the other types in the signature of fmap. A and b have the kind type because they are used as arguments and return types of functions. Fa also has the kind type because it's used as an argument to a function. Therefore, f has a kind type to type. Let's choose a data type and see if we can implement a functor instance. We need to choose a data type that has a kind type to type. Maybe fits the bill. We need to implement a function fmap, which takes a to b, maybe a, and returns maybe b. Here's one very simple and wrong implementation. We completely ignore the function, we ignore which maybe we got, we always return nothing. Let's try it out. It compiles successfully, but unfortunately it does not satisfy the first law. When we try to apply identity using our map maybe, we get a completely different result. This is a good example of how Haskell does not help us ensure that laws are satisfied, and why they are important. Unlawful functor instances will behave differently from how we would expect a functor to behave. Let's try again. This time we actually use both the function and a maybe. If the maybe was nothing, we return nothing, and if it had a value, we apply function to this value and return it as a just. This map maybe will satisfy the functor laws. For example, functor is a very important type class, and many types implement this interface. As we know, IO, maybe, list, and parser all have the kind type to type and allow us to map over their payload type. Often people try to look for analogies and metaphors to what a type class means, but type classes with names like functor don't usually have an analogy or metaphor that fits them in all cases. It's easier to give up on the metaphor and think about what it is. It's an interface with laws. We can use fmap to make a parser that returns single input or single output based on the parser that returns file path. And note that we can use either fmap as a function or fmap as an operator. Now that we have two parsers, one that returns parser of single input and the parser for single output, we want to combine them as options. Again, if we only had single input and single output, we could use a constructor for convert single to create options. So can we do a similar trick to the ones that we saw before with fmap? Does a function exist that can lift a binary function to work on parsers instead? One with this type signature, the one that goes from a function that takes single input, single output and returns options, to the one that takes two parsers and returns a new parsers for options? Yes, and this function is called lift a2, and it's from the applicative type class. Applicative, also known as applicative functor, has three primary functions. Applicative is another very popular type class with many instances. Just like any monoid is a semigroup, any applicative is a functor. This means that any type that wants to implement the applicative interface should also implement the functor interface. Beyond what a regular functor can do, which is to lift a function over a certain f, applicative functors allow us to apply functions to multiple instances of a certain f, as well as lift any value of type A into fa. You should already be familiar with Pure. We've seen it when we talked about I/O. For I/O, Pure lets us create an I/O action with a specific return value without doing any I/O. With Pure for parser, we can create a parser that, when run, will return a specific value as output without doing any parsing. The other two applicative functions can be implemented in terms of one another. Second one, apply, is actually more useful one between the two because when combined with fmap, it can be used to apply a function with many arguments instead of just two. To combine our two parsers into one, we can use either lift a2 or a combination of fmap fmap and apply. Note that both fmap and apply associate to the left, so we have invisible parentheses that look like this. So how did we get here? Fmap takes a function from a to b, a parser a, and returns a parser b. Specifically in this case, a is a single input and b is a function from single output to options. Apply takes a parser from a to b, parser a, and returns a parser b. Specifically here, a to b is single output to options, so a is single output and b is options. With fmap and apply, we can chain as many parsers, or any applicative really, as we want. This is because of two things, currying and parametric polymorphism. Because function in Haskell take exactly one argument and return exactly one, any multiple argument function can be represented as a simple function a to b. Applicative functor is a very important concept and will appear in various parser interfaces, not just for command line arguments, but also JSON parsers and general parsers, I/O, concurrency, non-determinism, and more. And the reason that this library is called optparse-applicative is because it uses the applicative interface as the main API for constructing parsers. We can create similar interfaces for convert directory constructor. We can create a parser for file path, which takes an input directory, and parser for another file path that takes an output directory, and combine them together into the options for convert directory. One thing we forgot about is that each input and output for convert single could also potentially use a standard input and output instead. Up until now, we only offered one option, reading from or writing to a file by specifying the flags input and output. However, we would like to make these flags optional, and when they are not specified, use the alternative standard input or output. We can do that by using the function optional from control applicative. Optional takes f of a and returns f of maybe a. Optional works on types which implement instances of alternative type class. Alternative looks very similar to the monoid type class, but it works on applicative functors. This type class is not that common, but often used for parsing libraries. It provides an interface to combine two parsers. If the first one fails to parse, try the other. It also provides other useful functions, such as optional, which will help us in our case. We can make the input file parser optional by using optional and use it together with from maybe. Notice the type of from maybe. We can extract an a out of maybe by supplying a value a for the nothing case. So either we have just of a value which we can just extract, or we have nothing and we use the supplied alternative or default value. So in this case, either we successfully parsed and extracted the input file, or we fall back to standard input. And the same for single output. Either we successfully parse an output file, or we fall back to standard output. Now we can use these more appropriate functions in the convert single options instead. We currently have two possible operations in our interface, convert a single source or convert a directory. A nice interface for selecting the right operation would be using commands. If the user would like to convert a single source, they can use convert. For a directory, they can use convert directory. We can create a parser with commands with subparser and commands function. Subparser takes command modifiers, which can be constructed with a command function as input, and produces a parser. Command takes the command name, in our case convert or convert directory, and a parser info, and produces a command modifier. As we've seen before, these modifiers have a monoid instance, and they can be composed, meaning we can append multiple commands to serve as alternatives. A parser info can be constructed with the info function. This function wraps a parser with some additional information such as helper message, description, and more, so that the program itself and each subcommand can print some additional information. Let's see how to construct a parser info. We use the info function, we pass our parser, which converts single, together with a helper, which adds a helper output screen in case the parser fails, and a program description, which just says that it converts a single markup source to HTML. And these are our first options. Let's also build a command. We use a command function. We pass it a string for the name which we decided is going to be convert, and we pass it the parse info we created below. Now we should do the same for the directory command. We create the parser info for the directory and the convert directory command. Now we can create a parser for options, combining the two options with subparser function. Subparser takes both the command modifiers for the single input and directories and produces a parser. You might notice that most of the screen is taken by the variables and types. If you prefer, we can combine all of this into the parser without using intermediate parts. And since we finished building a parser, we should wrap it up in a parser info and add some information to it to make it ready to run. We create a parser info like we did before. We pass a parser, additional helper, but this time we add full description, header, and a prog description. And finally, running a parser. Optparse-applicative provides a non-IO interface to parse arguments. But the most convenient way to use it is to let it take care of fetching program arguments, try to parse them, and throw errors and help messages in case it fails. This can be done with a function execParser, which takes parser info and returns an IO. So the interface to our module is going to be parse, which parses command line options. We should expose this function together with all the data that it uses or provides. Options, single input and single output. After running the command line argument parser, we can pattern match on our model and call the right functions. Currently, our program does not expose this kind of API. So let's go to our HSBlock module and change the API. We can delete main from that file and add two new functions instead. Handle is an IO abstraction of a file system object, including standard input and standard output. Before, we used write file and get contents. These functions either get a file path to open and work on, or they assume the handle is a standard input-output. We can use the explicit version that takes a handle from the system output instead. Convert single takes a title, the input handle, and the output handle. First, we read the content from the input handle, then we process this content using the path title and put it or print it into the output handle. We will leave the convert directory unimplemented for now and implement it in the next chapter. We can clean up the rest of the HSBlock and move to the main. In the main, we'll need to pattern match on the options and prepare to call the right function from HSBlock. We cannot just call main as we did before. First, we need to bring the dependencies. Now we have to use the new optparse module and re-import some system modules. Note that we need to add the dependency directory to the executable because we need to use this library in main. So what are we doing now? First we parse and get the options, and then based on these options we match and see. If it's a convert directory, we call the convert directory function, which doesn't do anything right now. But if it's convert single, we have to deal with inputs and outputs. First we look at the input. If it's standard input, that we know that input handle is standard input and the title is empty. And if we pass the file, then we have to open the file, read it, from which we're gonna get the title and the handle to the file. And for the output handle, we pattern match again. If it's standard output, it's easy. We just pass the handle to standard output. And if it's an output file, we check if the file exists. Then we ask for confirmation if the file exists or not. And then either we open the file and get the handle or return the exit failure because it's not allowed. And at the end, we convert the file from input to output using the handles we just created and closed all the handles at the end. There is another small change that we need to do in the Cabal file. We need to list the optparse in the list of modules in the executable. Now we can see the results of running our block generator with the help command, which shows us available options and available commands. In this part, we've learned about a new fancy library called optparse-applicative and used it to create a fancier command line interface in a declarative way. Along the way, we've learned two powerful new abstractions, Functor and applicative, as well as revisited an abstraction called monoid. With these libraries, we've seen another example of the usefulness of these abstractions for constructing APIs and EDSLs. We'll continue to meet these abstractions in the rest of the book. In the next part, we'll process multiple files in the directory and learn about error handling in Haskell.